Chapter 1, Gravitation. We all know that the gravitational force is a universal force and it acts not only between two objects on the earth but also between any two objects in the universe. So let's see what is meant by gravitation. The phenomenon of gravitation was discovered by Sir Isaac Newton. He discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not at an angle to the vertical. Why do they not fly off in a horizontal direction? So he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is the vertical direction at the position of the apple, and thus the apple falls vertically downwards. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much farther away from the earth? Yes. To find this, let's see about force and motion. We know that a force is necessary to change the speed as well as the direction of motion of an object. So let's see about circular motion and centripetal force. Tie a stone to one end of a string and take the other end in your hand and rotate the string so that the stone moves along a circle. As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle, and are applying a force towards it. The force stops acting if we release the string. In this case, the stone will fly off along a straight line, which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. Thus, a force acts on any object moving along a circle and it is directed towards the center of the circle, and this is the centripetal force. The moon, which is the natural satellite of the earth, goes round it in a definite orbit, and the direction of motion of the moon as well as its speed constantly changes during this motion. That means there must be a force which is exerted on the moon, and this force must be exerted by the earth, which attracts the moon towards itself. Similarly, the sun must be attracting the planets, including the earth, towards itself. Then Kepler's laws. By the 16th century, a lot of data were available about planetary positions and motion. Johannes Kepler studied this data and noticed that the motion of planets follows certain laws. So, Kepler's first law: the orbit of a planet is an ellipse with the sun at one of the foci. Here we can see the elliptical orbit of a planet revolving around the sun and the position of the sun indicated by S. An ellipse is the curve obtained when a cone is cut by an inclined plane. It has two focal points. The sum of the distances to the two focal points from every point on the curve is constant. So, if F1 and F2 are two focal points of the ellipse, and if A, B and C are 3 points on the ellipse, then AF1 plus AF2 is equal to BF1 plus BF2 is equal to CF1 plus CF2. Then Kepler's second law: the line joining the planet and the sun sweeps equal areas in equal intervals of time. The straight lines AS and CS sweep equal area in equal interval of time. That means the area ASB and the area CSD are equal. Then Kepler's third law. The square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is the period of revolution, then t square is directly proportional to r cube. That means t square upon r cube is equal to constant is equal to k. Then Newton's universal law of gravitation. According to this theory, every object in the universe attracts every other object with a definite force, and this force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. So, here we can see two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies is written as F is directly proportional to m1 m2 upon d square, or F is equal to g m1 m2 upon d square. Here g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. But if the bodies are not spherical or have irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between the two centers of mass. So from this equation, we can say that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. In SI unit, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The unit of g in SI is Newton meter square per kg square, and the value of g is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Then uniform circular motion, that is magnitude of centripetal force. Consider an object moving in a circle with constant speed. Such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle, and this is centripetal force. If m is the mass of the object, v is its speed, and r is the radius of the circle, then this force is equal to F is equal to mv square upon r. If a planet is revolving around the Sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the Sun must be F is equal to mv square upon r, where m is the mass of the planet, v the speed, and r is its distance from the Sun. The distance travelled by the planet in one revolution is the perimeter of the orbit, that is 2 pi r, where r is the distance of the planet from the Sun. Time taken is the period of revolution, that is t. So v is equal to distance travelled upon time taken is equal to 2 pi r upon t. F is equal to mv square upon r is equal to m 2 pi r upon t bracket square upon r is equal to 4m pi square r upon t square. Multiplying and dividing by r square, we get F is equal to 4m pi square upon r square into r cube upon t square. According to Kepler's third law, T square upon R cube is equal to K. Therefore, F is equal to 4m pi square upon R square K. But 4m pi square upon K is constant. Therefore, F is directly proportional to 1 upon R square. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the Sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. And this is possible because of the huge masses of planets, stars, and other constituents of the universe. Then Earth's gravitational force. The Earth attracts every object near it towards itself because of the gravitational force. The center of mass of the Earth is situated at its center, so the gravitational force on any object due to the Earth is always directed towards the center of the Earth. Because of this force, an object falls vertically downwards on the Earth. Similarly, when we throw a stone vertically upwards, this force tries to pull it down and reduces its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downward towards the center of the Earth under its influence. Then Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it, and according to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the Earth on a body results in its acceleration, and this is acceleration due to gravity, which is denoted by g. Acceleration is a vector. As the gravitational force on any object due to the Earth is directed towards the center of the Earth, the direction of the acceleration due to gravity is also directed towards the center of the Earth, that is vertically downwards. Now, value of g on the surface of the Earth.